Today's talk, for those who heard yesterday's talk, it's going to be very different. It's going to be more technical. 2 slides from yesterday, and then we'll go into technicalities. I really want to emphasize the usefulness of very important or very sophisticated mathematics into the use of medicine, which I believe is what was just mentioned. And so we'll today talk about this part of mathematics. It is useful for a lot of aspects. So you see here my, is there any pointer by any chance? You see here my university website where all my publications are. So if you want to follow any of the publications, you're welcome. There's a little echo in the loudspeaker. Usually I'm talking quiet. Okay, so you can definitely check there. The work that I'm describing here was done while I was in the university, in Tel Aviv University. I'm in computer science there and neuroscience. My background, as you will probably see soon, is in mathematics. So let's just go back to a slide of describing the problem that we are trying to solve, and from there we'll see how we want to address it. So we want to monitor the most complicated organ that we have, which is the brain, and obviously that's a very complicated organ. There are some scanners which are actually not very old, so the functional MRI was invented only in 1985. Before that, we had MRI, so the magnetic issues were known before, but the real functional part, namely monitoring the brain as it is active, not just the status or the structure, but actually the dynamics, is only from 1985. If you think about it, it's a very simple machine because it tells you every 3 seconds what amount of oxygenated blood is arriving into different areas in the brain, which is kind of not a lot of information of what's going on in our brain, but the thousands and thousands of papers that have been written on the brain since do indicate that this took us forward. We want to really go to something like continuous, like the glucose monitor, okay, which monitors something very simple, the level of glucose in the blood, but apparently it's very, very useful for managing diabetes. And you can imagine that when you have problems with the brain, therefore you need, of course, a continuous monitor to supply different medications, to see the effect of medications, etc., etc. So these are the 2 devices that are still being used. We want to go to something much simpler, basically a patch on the forehead. So history of a specific part of signal processing, which is based on harmonic constraints. So that's harmonic analysis. A big chunk of it was developed for analyzing seismic data. And if you think about it, seismic data and monitoring the brain are really very connected problems. The sensors are different. It's not seismic, it's electric, because the brain is emitting electric signals. But again, you're sensing something on the surface, and you're trying to understand about something that happens inside the brain. And while we have not yet solved the problem, and we cannot predict earthquakes very accurately and robustly, elephants, for example, did solve the problem. So elephants have seismic sensors in their legs. This is actually how elephants communicate with one another, but they can sense that an earthquake is about to come, and they're actually even trained to go to the mountains because I guess somehow they know that there may be a tsunami coming with an earthquake. So obviously the problem can be solved, it's just that our brain has not yet solved it. And that's what we want to address. I'm actually dealing with earthquakes as well, but of course today we'll talk about EEG. So Fourier, which all of you are familiar with, is really 250 years old. Okay, actually started even before Fourier, but then the Fourier name was given to it. The real DSP, or digital signal processing revolution, started in 1967, when it turned out that one could do fast Fourier transform, FFT, at n log n, where n is the number of points that you want to analyze. So this was really the mark of switch of signal processing from actual capacitors and resistors and coils to digital, and really the birth of the analysis that we do nowadays. So n log n, for a single basis, that was the fast Fourier transform. Then 10 years later, the wavelet decomposition, which again at n log n would find a wavelet decomposition of the signal, and we are talking about orthogonal decomposition of signals with harmonic constraints. The real jump in this field happened in 1992, but still a lot of people are not aware of that. So now, after this work of Kaufman and Wickerhauser, it was possible to do in order of n log n time a search in something like 2 to the power of n possible different decompositions of the same signal and choose the optimal one, okay? So this is why it's a huge jump, because not only a single basis, but now choose from a huge number of possible bases the one that fits the data the most, okay? So I'm gonna talk about that very soon. I'm gonna try to give the highlights of this algorithm. And then we modified it a little bit. 10 years later, we modified it a little bit to optimize also on the mother wavelet. So this is optional for wavelet and wavelet packets, which is what the best basis algorithm relies on, okay? So these are the things that I'm going to talk about today. So the papers that you know, since you want to go into this field or want to get an idea, so this Dobishi paper from 1988 is a very good paper to start with, okay? It gives the kind of fresh, for those days, construction of wavelet. I'll put all the references at the end for those of you who would want to see. Only 7 references, so you can take a picture then if you like. Anyway, so this is the construction of compact support orthogonal decompositions, and I'm going to rely on this paper. But I'm not going to go too much into wavelets, because I kind of assume that you're familiar with wavelets, so I'm just going to take us a little further to this paper, this 1992 paper of Kaufman and Wickerhauser. This is a very, very short paper and very difficult to read. So that's why you want to start with Dobishi and then go to this paper. So let's go into the details. The first thing is this construction of cover of the space, and he constructed a very simple cover of this type so that these two sons, the left and right children, actually, if you sum them together, you get the original cover, and you get so you get stages or steps where you first cover a big chunk, and then you cover a smaller chunk and a smaller chunk, and this is the construction of doing that. Then, given any specific function, for example, a sine with changing of frequency and location, then we can actually cover this space by multiplying one by the other and getting this construction, which will be the basis of this orthogonal covering of the space. Okay, this orthogonal covering will come in many times. It will help us optimize the search and really be a key, so we'll go into it more and more. By the way, if there's questions, you can raise your hand, stop me and ask during the presentation. Any questions so far? Okay. So then we need one more thing, in order to construct a basis function, and this is the quadrature mirror filter. I don't know how many of you are familiar with it. Again, you can see the mathematical constraints that it is producing, that it is obtaining in this Dobishy paper, and this basically is the tool to create wavelets. So in the Haar wavelet, the simplest wavelet, we have what's called the sum and the difference, okay? Or basically the average or the low pass and the difference, which is the high pass. And the quadrature mirror filter is producing, in general, this high pass and low pass in the more general way, not just in a Haar kind of representation. So these are the constraints that it has to satisfy. And when these constraints are satisfied, then we can create a wavelet. So these are the two functions that are being created from this quadrature mirror filter, and this function g that we modify or that we define from h, where we only have to describe W0 and W1. So W0 is the scaling, and W1 would be the mother wavelet of our wavelet representation. Okay, so the mother wavelet is a function that has to satisfy some constraints. Basically, we like to build wavelets, mother wavelets with vanishing moments, so kind of the expectation of the third, fourth, fifth moment of the function goes to zero, and those turn out to be good mother wavelets. But again, when there's a specific data with specific statistical properties, it is possible that another specific mother wavelet would be most appropriate. And of course, you know that there are many mother wavelets which suggest that for different types of problems, you will have different ones. Okay, so to compress images, there's a mother wavelet, but if you try to use that mother wavelet to compress radiological readouts or X-rays, then that mother wavelet kind of kills the signal completely. While it compresses the signal, the tumors will be totally gone. So it's obviously not cannot be used for this kind of thing. So we have now basically the construction with these W's of the mother wavelet, and with this we can construct this wavelet packet tree. So wavelet packet tree is the extension of wavelet representation. Wavelet representation, as we shall see, is basically the low pass remains, then the high pass is being kept to produce again the low pass and high pass. So this low pass remains, and then again the low pass here remains, and this will be the wavelet representation. But it turns out, and this is what Kaufman showed, that you can actually create this whole representation. So you can keep the high pass, keep the low pass, and you can actually, from the low pass, you can again continue and decompose it. Okay? And why do we want to do that? We want to do that because this gives us a much larger variety of orthogonal decompositions. While this is one orthogonal decomposition, as I described, in fact, for example, this line is a full orthogonal decomposition. And how do you see that? Basically, because it spans the same space, it covers the same space because of orthogonality and because of the same number of basis functions, then it has to be an orthogonal decomposition that fully covers the space. Okay, so it's kind of quite simple to see what is going on. So basically, every covering of this wavelet packet is one possible orthogonal basis of our data. Okay, now the number of levels is log n when n is the signal. So if we start with, say, 2048, we want it to be a power of 2. If we started with 2048, we can go all the way 12 levels down. And of course, you can see then that the variety of bases is very, very large, okay? So as I mentioned, this is the classical wavelet representation. And then this is another cover, and we now want to find a way to find the best cover, okay? What does it mean to find the best cover? To find the optimal cover for a specific signal, and in fact, it can be for a specific group of signals, okay? So this representation, this wavelet packet, does anyone have any idea of how one can create a wavelet packet for a collection of signals out of it? Okay, so basically, you know Parseval equality? Let's see, Parseval equality. It's Russian, should know. Okay, so basically we know that when we have an orthogonal decomposition, okay, basically the variance of each projection is additive and adds to the variance of the whole signal. We are talking about the final signal here, so it's simple. Okay, and now when we take a collection of representations, okay, then we can split the data into windows of a certain size, and we can decide if we go across windows with any kind of overlap. And from each window, we can create such a wavelet packet representation. Okay. Now, if you want to take the average of this, we do not average the representations because it would have been linear and it would be averaging the original signal, but we average the square of the signal, so we kind of average the contribution to the variance of each one of the representations, and then that average provides now a single wavelet packet representation for the collection of signals. And again, from this Parseval, you can understand that if you find a specific, let's say, basis which contributes a lot to the variance, then it actually contributes to the expected variance of all these windows. So it can easily be expanded into a collection of signals, which is really what we want, because we want to create statistics or create a new representation for a large collection of data that we have not seen before. Okay, so I should mention, since you are in Yandex and you're doing machine learning and you're extracting features from data, I hope all the time, so you may be asking yourself, well, why do we need this? Okay, we have our machine learning, we have our very strong computers, we can take the data and we can find a way to optimize, and we can find the same features, and we don't need all this harmonic analysis. So it turns out that this is not true. Namely, the constraints, or what would be called in statistics, the biasing of the model that is built into these harmonic constraints, will find a much more optimal solution when the assumption is correct. Namely, when the assumption that the signal is harmonic, okay? Kind of like a combination of cosines and sines in simple terms. Okay, so when the constraints are satisfied, this will find a solution with much less data. And although nowadays we have a lot of data, it's still not enough to find the optimal solution just like that. Okay, so you don't want to do what Google is doing, that they're taking all the YouTube data together and then trying to find a feature of a cat, something that a kid that is 1 year old, after seeing three cats, has already done, okay? So that kid has many more constraints which enable him to find features of a cat, whereas Google is trying with tens of millions of pictures to try and find features, and that is, of course, not comparable to building the right bias. So here we are building the specific bias for specific signal processing. That's very important. Okay, so we want to move to any cover, and we actually want to understand the best basis algorithm, okay? So we understand that each such cover, for example, this covers this part, these two cover this part, so this is an orthogonal decomposition of the same signal, okay? And we want to now devise a quick algorithm to choose that. So we have the line at the bottom, which is a very simple way of looking at entropy of coefficients of a vector, okay? We take the vector, all the vector coefficients, we actually normalize them by the norm of the whole vector, so we kind of convert it into a probability, and we now calculate the Shannon entropy of the coefficients of this vector, okay? When we do that, we kind of get something that resembles the dimensionality of the signal, okay? Again, we want to do it on a collection of signals, so we don't want to just be looking at too few, but once we do that, we actually get now an indication of how varied the signal is, okay? You can understand that if only one projection is high and all the rest are zero, then the dimensionality is 1 or very low, and again, when these are like uniform, then the dimensionality, the span of this space is much larger than the dimensionality of the original space, okay? That is kind of the idea. And once we do that, we can look at every projection and ask what is the dimensionality or what is the entropy of that projection, or what is the entropy of the coefficients once I project them on this function of the orthogonal decomposition, okay? So what would I be looking for? Low entropy or high entropy in these projections? What would low entropy mean in these projections? Stand up. And Exactly. Very good. So you're probably familiar with principal component analysis. Okay, that's like the simple two-dimensional, Gaussian kind of assumption of the data. Then principal components do find the variance in different directions. Okay, and then we want to project the data onto those directions with high variance. Correct. So we kind of try to compress the data onto those projections where we have high variance that, again, with Parseval equality, is giving us the contribution of the contribution of the variability in the original data, and have the other projections be with low variance, or in this case, with kind of probability small, so the distribution would be large for few coefficients and small for other coefficients. This is if we rotate the projection to find the optimal variance, which principal components do. This is kind of the same idea, but not necessarily with the assumptions of Gaussian distribution. So we talk about entropy and we don't talk about variance, okay? Entropy is being maximized in a Gaussian case when you're not bounded from left or right. Okay, so it's a signal that is in L2 but is not bounded. Then Gaussian maximizes the entropy. Here we are talking about a different distribution because we are bounded. Okay, so we want to again minimize the entropy just like we would do in principal components, and then we can basically look at each one of those and ask which ones minimize the entropy. Now Kaufman came up with the amazing idea of starting bottom up and looking at these two projections which are the children of this representation, and asking, well, which one has lower entropy? These two together or this one? Okay? And if these two have lower entropy, then we keep these. If this one has lower entropy, then we would keep this one. Okay? So we are starting bottom up. We are making all these comparisons at the same time. Why can we compare these two and it is totally independent of what is going on here? Again, because of the orthogonality. Okay? So these two are totally orthogonal to what is going on here, and therefore I can make a decision here without wondering what is going on here. So the algorithm can actually go and do these decisions and not have to kind of change the decision whenever something else is changed. So if I choose this, that affects nothing here. So I would compare these two to this one. I would compare these two to this one. And then I decide which one of them I keep, and then I can go up. So if, for example, this and this was chosen, I would then compare it to this and see if the entropy of this projection is lower than the entropy of these together. If so, I will choose this one, otherwise I would keep this. So now you see that the number of comparisons is actually very low. It's exactly n log n. Okay? And this is why you can choose from a huge number of possible bases the optimal one in n log n time. Does this make sense? And you see that it's kind of like wavelet, but extension of wavelet, okay? It's because wavelet is not adapted. Wavelet is one, okay? It's this basis. Here, we can choose the one that minimizes, that really minimizes the entropy. And because of this degrees of freedom, we can really fit this to the data in a very, very nice way. And Kaufman has a lot of examples in many papers, chirp and all sorts of signals which change in time and frequency. Of course, a signal that does not change in time is this useful for it? Like a combination of two sine waves. Everything that I'm saying, is it going to be useful for it? No. In that case, simple spectral analysis, simple bandwidth of the two frequencies that I'm listening to will be enough. But when we have dynamics in the signal, okay, when the signal changes in frequency and time together, when there's dynamics, then this becomes much, much more effective, okay? And unfortunately or fortunately, all the signals that we really look at have this kind of dynamics, okay? I did not say where this has to do with the brain, but you understand that in the brain you have different regions which produce kind of oscillations of a large collection of neurons in that region which are active. So if I'm recognizing a face, there's an area that is recognizing faces, and then in that area there's an area that's recognizing the eyes, the nose, the forehead, the chin, etc. And they're all firing together to kind of say, oh, this is my wife, okay? So this oscillation has, of course, a lot of dynamics until I decide, okay, it's my wife, and I move on to do something else with my brain. And during that time, it's a very specific dynamics that one can recover in this way. And if we do this kind of decomposition, then we can listen to the brain with kind of one microphone or just one electrode or the difference between two electrodes, and we can listen to the whole symphony of the brain, and by applying this kind of decomposition, we can actually find the different dynamics in different regions and extract those as features that tell me, now it's the facial area that is active, now it's me planning a movement, now it's my mood that is becoming happier, and therefore a certain region, the limbic system, is now active, and things like this, okay? So we are trying to kind of do whatever each one of you is doing at their early age when they go to listen to the symphony the first time. There you have a little bit of additional information because you look at the symphony and you see the violin moving, and you also hear, so you make the the association. But let's say you never went to the orchestra, you just listened in the loudspeaker at home, you would still start to separate the different musical instruments based on the different dynamics of each one of these instruments, and this is a tool that does that. Actually, our brain does it still better than this system, so there's room to improve, but this is already a nice progress. Any questions so far? Okay, so we move on. So now I want to talk briefly about a slight modification that we did to this signal. I'm going to rely on a paper, on a book. So this is kind of a technical, quite involved paper. You can download it from my website if you want to. It relies on this book of Gilbert Strang and Trung Nguyen. It's pronounced Nguyen. Okay, he's now in UC Santiago, Nguyen. This is, by the way, the book that you get when you get MATLAB Wavelet Toolbox. So you may find copies of this book for those that have the MATLAB Wavelet Toolbox. Nguyen came from engineering as opposed to mathematics, and therefore he was able to reformulate wavelets more like filter design that comes from engineering, and this is the key tool that we are using here. Okay, so what is it that we are trying to do? We said that we optimize the basis, okay, for a given mother wavelet, okay? And now we say, well, but it's a given mother wavelet. Maybe we can optimize the mother wavelet for a given collection of signals, okay? So the trick would be the following. We start with a certain mother wavelet, or with a location in space of parameters. We find the best basis. We then apply the technique that I'm going to show now to move down the gradient of this total entropy to find a better mother wavelet to reduce the entropy for this given best basis. And now, with the new mother wavelet, we can again reapply best basis, and maybe the basis will change, and we can repeat this process, kind of like in the EM algorithm, until we converge, and we cannot modify the mother wavelet, and we cannot modify the basis. Does that make sense? Okay. There's only one problem, and the problem is that the mother wavelet, as you've seen, has to satisfy a lot of constraints. Okay, to be called a mother wavelet, it has to adhere to this quadrature mirror filter, etc. Okay, so we could either do the gradient descent with a constrained gradient descent and kind of put all the constraints to minimize, to optimize the mother wavelet, but we actually found another way, because in what Trung showed in this book, which was in 1996 and 1997, the second edition, he actually showed a factorization of the whole wavelet packet representation with matrices that are constraint-free. So basically a reparametrization that for every parameter you get a mother wavelet out of this representation. And therefore, the gradient descent becomes very, very simple because it's not constrained. As you know, constrained gradient descent is much more complicated than non-constrained gradient descent. So we were able to do it, and then it became mathematically, one, feasible, and two, quick to actually really do it. So what do we do? As I said, I'm jumping to equation 31 in that paper, and of course you can go back to the previous ones. Basically this lattice method, which Trung and Gilbert Strang, his teacher, introduced, actually shows this lattice reparametrization of the wavelet packet into matrices, okay, kind of very simple matrices where each kind of packet actually is factorized into a series of matrices with a parameter theta. This is the parameter that we want to optimize, so that the total representation is basically this large multiplication of all these matrices. So again, it's not trivial, and I cannot go into how we got to this, but from the paper, chapter 5, at the paper of the book of strength, and that paper that we wrote, you can actually recover the whole thing, and it's actually quite, once you spend a lot of time in it, you see it's quite simple. Okay, so it's really a reparametrization, especially if you come from engineering and you know this way of representing filters, you see that it actually came from that idea. And once you do that, then all that is left is to do the optimization. To do the optimization, you kind of calculate the Jacobian, or you want to differentiate this collection C with the different parameters theta 1 up to theta k, which are given for every mother wavelet that you start, or for every point. So now you are kind of optimizing in a space of k dimensions to find the optimal mother wavelet. Okay? So I emphasize again, you take a large collection of data sets. For example, we collected EEG from many, many people. Okay? Then from each person, you divide the data into chunks. For example, we use chunks of 2,048 points. We sample at 500 hertz, so 500 times a second. So this is basically giving us 2 seconds of data. Again, we want to be power of 2, so 2,048. Okay? And now you have a very large collection of windows of signals of 2048 from many people doing many different tasks. And from this now you want to find the optimal statistics of this specific data, and you understand that it will be very different than the music, than the trumpet, okay? And in order to do that, one can then find best basis first, and then modify the mother wavelet, for example, with this method, and until you converge onto the solution that is satisfactory. And that solution is optimal in the sense of entropy, namely it really captures, just as you said, it really captures the essential features of the signal that you are working with, and therefore it finds features that are indicative of what is going on. So just to compare it, because you're studying statistics and machine learning and everything, what we didn't do here, we didn't do the most obvious, which would be, take a bunch of people that have a specific disorder, take a bunch of what we call controls, give them labels, and now run certain machinery, which will find, based on, in the simple case, logistic regression or factor analysis or any other statistical method that tries to separate between two data representations and find, okay, this is a hyperplane which separates between, of course, deep learning, etc., whatever you like to do. And then we find a hyperplane which separates between the healthy and the sick, and we are happy we can predict or we can automatically detect if they are sick. So we did not do that on purpose, because we first wanted to really understand the data or learn the statistical properties of the data. So we did not use labels at all. We took all the data together to find kind of the statistics or to find features that resemble this data. And now from the processed data, namely from these projections, now we can do anything we want. We can take label data after the projections. This is kind of a new representation of the original data, but a representation that is much more compact. And now we can apply everything we want. So the first stage, we apply this, now we project the data, and now in the new representation we apply all sorts of detectors for specific abnormalities that we are looking for. That's kind of how we did it. We first did what's called unsupervised pre-processing, but pre-processing not just factor analysis or principal components or independent components, but we did this kind of pre-processing, harmonic analysis-based pre-processing, and on these projections we are now looking for specific predictors. Okay, make sense? All right. It does make sense to do unsupervised dimensionality reduction at the beginning because you don't want to be biased to specific labels. You probably have seen or are familiar with the problem of overfitting. Bias variance decomposition of signals. Okay, so we always have not enough data. Because basically whenever we have more data, we increase the number of degrees of freedom of our model. So we are always with a model that can be too complicated for the data that we have, and we have to put constraints. Okay? So if we try to put labels and try to do the separation, we find very quickly that we separate the training data very, very easily, but prediction on new data actually does not work so well. Okay? For example, in gene analysis, you have 100,000 genes, you find 5 genes that separate the data perfectly, you then go to a bigger population or to a test set, and it turns out that it doesn't work. So reducing dimensionality in an unsupervised way is a very good way to do it. That's basically it. Any questions on what we've seen? Too quiet. Muchnik, any question? So just for all that are interested in the references, apparently there were very few references in 2002. Basically Kaufman and Wickerhauser and Nguyen, this digital filter bank. That's another paper of Nguyen, but the book is here, Gilbert and Strang, and Dobishi that I mentioned before. And we worked on it with Rafi Kaufman and with Trung Nguyen, so they kind of were very instrumental in helping us produce this kind of optimization. So that was certainly nice. Okay. So just I'll finish with a couple of examples again of the algorithm on what we are doing, with EEG. But you can imagine that this can be useful for any kind of harmonic data that you're looking at, speech, for example. Okay. So I encourage you to try it. It's not so trivial, but definitely you can do the best basis. We could consider helping with the optimization later, but you may find it extremely useful for a lot of different types of data. So now, kind of this, I believe that the list of lines here is more clear. Okay, we start with a large cohort of EEG recordings. Using Kaufman, we create best basis, this optimization, so we do it a few times. Denoising with Donahoe, the classical denoising technique of wavelets or wavelet packet analysis is the same. Basically, you take the very small coefficients and you equate them to 0. You forget about them, so it's no big deal. We did something specific to our representation, which is reorder the representation. So we did not keep the classical order of the tree, but we actually moved the different projections, the different sub-basis functions. We moved them so that they would be geographically close to one another when these two features are highly correlated. Okay? They cannot be too correlated because we know they started from orthogonal representation, but they may be partially correlated under specific cases. Okay, so if we found, for example, that happiness and stress have something in common and then two features that are not common. So one common is more correlated to kind of extreme feelings, and apparently it does not make the separation between stress and happiness, but when we go to more features, we actually see that. So the three together tell us, oh, this is active, so it must be either happiness or stress. This is active, it means stress. No, this is active, it means happiness. So we put them together based on the correlation between them, and that created a representation that is kind of much easier to look at. And yesterday we looked at many such representations. I'm not going to go into this today. So this is this reordering, and this is all done in what we call offline. Then when we have new data in real time, we project onto this reordered basis that we found before, and we calculate the energy in each, and this is what we are presenting. And maybe just one slide of this, and this is a slide I showed before. So the offline part is here. We collect the data, a large cohort, it's here, the database. We create these basis functions and we reorder them. And now when we have new data, we actually project onto this ordered basis functions, and we get this kind of representations. And I believe we've seen a lot of those yesterday, so I'm not going to show more today. And as I mentioned, once we have that, we can apply another engine that actually looks at representations like this and actually creates letters, words, and grammar from this representation, okay? So now this actually, we can look at it as a new language of the brain, which would be in music, would be notes, or any other language, MIDI, any other language of music, okay? So we are creating a new language of the brain with this, so that we can actually create more sophisticated detectors. And you can now imagine that a sick brain may have lower entropy compared to a healthy brain, okay? For example, an anesthetized brain is very low in terms of activity, so it's obviously not doing too much, and therefore it will have a very low entropy. So now you can actually analyze the entropy of this new language, and you can in fact apply a lot of tools that you're using nowadays to analyze text. You can actually apply to this new representation. Once you convert this detailed brain activity representation into words, and we are now looking at 80 letters in this alphabet, not 22, not 26, but 80 letters, okay? Once you convert it to this new text, you can really do a lot of text analysis, but with brain data. And this is really what we are trying to do. So we are trying to build a large database, and we are trying to see when the language is more advanced, less advanced. I don't know if you're familiar, for example, there's a famous article that was comparing the entropy of language between two newspapers in the United States, one USA Today, which is kind of simple language, and one Wall Street Journal, and found much higher entropy in one journal compared to the other, okay? A lot of people did that with Shakespeare, etc. And we are going to do it with the brain. Okay, to analyze specific states, to analyze specific cases, to understand both the dynamics, which I call the grammar, okay, and the amount of words and language that the brain produces. Okay, so on this note, I'll end. Thank you. Question there.
Okay, so my question is, so you're listening to this like symphony of the brain, right? And how can you be sure that, so you say that you take the lowest entropy decomposition, right? But how are you sure that it is the right decomposition? So for instance, if it's like musical instruments, you have like multiple pianos, and like the same signal can be produced by two sets of different pianos. And is it because your basis functions are so different, and you can be sure that this decomposition is really the correct one?
Okay. So you're asking a very good question. So at the beginning I thought, well, this is a very powerful technique, and I would actually apply it to every person separately, because one brain is very large, one brain is small, let's say a child, so the dynamics should be different, and of course, why would the statistics of this brain resemble this brain? And I thought that I would apply it, and then of course, if I'm going to deal with sick brains or healthy brains. But then it turned out that apparently, with magic, they actually reorder themselves, and there is actually a representation or a basis function that seems to be fitting a lot of brains, okay? And of course, if I would go to deal with a very, very specific problem, it's possible that the statistics there is even more refined, and I would benefit more from building this kind of machinery onto that small group. But for the beginning, I wanted to create a representation that can fit as many brains as possible, basically do a pre-processing that fits all. And the big surprise was I was actually doing a lot of work with dogs, trying to read the same thing from dog's brain, and I could not put the electrodes in the same location as on humans, because on humans we put it here, on the dogs we had to put it here because this would like not let their eyes kind of see, so we had to put it in a place that's a little easier. And I thought that obviously I would create a different representation for the dogs than for humans. I collected a lot of data on dogs, I collected a lot of data on humans. I did this, and then I did both, or actually I just did humans and I compared it to what turns out with dogs. And it turns out that the same detector for happiness that we had for humans worked very well on dogs. And really what we wanted to find in these dogs is happiness, so there was no point to do a happiness dog on dogs. And a few months ago, I don't know if you heard, but someone managed to train his dog not to move when he goes into the functional MRI, because in the past they were only putting kind of sleeping dogs or anesthetized dogs in the MRI, but he wanted a functional, or he wanted the brain to be functional while in the MRI, so he put his dog in the functional MRI. And the doctor said that the activity of the brain of the dog resembled the activity of a little child, and I would say it resembled the activity of a very smart person. Okay? This is really what I felt. I could see that the activity of the dog's brain and the activity of human's brain were quite similar, and definitely for what I wanted. So it turns out that there's no need to do that, and really this is when I kind of decided to start a company, because it looked so crazy that it's either stupid, so I tried another 2 years, kind of tried everything possible, and when I could not find any bug, I decided to start a company, okay? Yes. Yeah.
Thank you very much for this very nice presentation.
Thank you.
Well, I can tell you I'm a little bit confused. Well, actually not a little bit, but quite a bit confused. Well, if you go to the technical part of it, okay, I'm a little bit... Okay, so let's put it this way. You are talking about wavelets, right? And first of all, when you just started your talk and you started to talk about the 2-second signals, right?
Windows.
Windows, right? 2-second windows. And then I said, well, wavelet packet decomposition is not time invariant. Okay, right? Because if you shift it, you get slightly different set of coefficients, right? But then, okay, you overcome it by...
Good point.
But just a second, just a second. You then overcome it by looking through many signals, and well, they come all in different phases, and then all you end up with, basically Fourier decomposition, because you just measure in the presence. Well, yes, indeed, those are not just, well, I mean, you're losing temporal information here. And so the reason why I think that you are getting things which are so similar, you're just getting alpha rhythm, you're getting beta rhythm, you're getting 1/f structure of the human EEG, for instance, or dog's EEG, or cat's EEG, or horse's EEG. Mm-hmm. So this is A, right? And so, like, on one hand, I see that you aren't. Well, I'm not aggressive at all. I'm just really not understanding what's happening.
I think I have an answer. So don't
try
worry.
to answer, please.
Yeah. Okay. So you see, we are looking at 2-second windows, okay? We are sampling at 500 hertz, okay? So we actually have a lot of changes there, all right? And now we average, correct? Because we kind of average on the two windows.
Average powers, right?
On these 2 seconds, okay? So if there is a certain small dynamics during these 2 seconds, okay, we will catch it because we average, okay? It will be it will jump out. Do you understand this dynamics? Because we are kind of creating filters for this dynamics, okay? Basically, each one of these orthogonal bases is kind of a filter for a certain dynamics, correct? We agree on that?
But the question, yes.
Okay.
So
And
for
now-
each 2 seconds, you have your own basis, or you have a basis for many 2 seconds?
I have a basis for many, many seconds. But for example, take a trumpet, okay, and see how the signal is produced. Then there's a certain time that you kind of attach the lips to the trumpet, and that creates a certain dynamics, okay?
Yeah.
And if you ask people, how do you distinguish between trumpet and a violin, which have the energy on kind of the same frequency band, it's really this dynamics that changes. On a guitar, you know, the first time you touch the string creates a dynamics, okay? So each one of these wavelet packets is basically a detector for a certain dynamics. And now it will look for this dynamics in all these 2 seconds, and it doesn't really matter where they are, because if this dynamics is there, it will jump. Because it is a very, very specific detector, you know, it will kind of not be sensitive to the rest of the signal. And this is why suddenly those features jump, even though I started, and you correctly noticed, I kind of scrambled the dynamics by moving a window without being, you know, like ERP, without being locked to I do this kind of things all the time. I did it in a paper in 1988 when I kind of made a distinction, and some people might like that paper because it was totally crazy. We were giving some military signals, and we were giving data of whales and porpoises. It's kind of crazy, but so between the two, there's a lot of shrimp noise. Now I'm telling you what's going on in the ocean. Extreme shrimp noise, whales, porpoises, and we were able to separate those very, very well. In fact, we were able to train on whales and porpoises in one ocean and separate from whales and porpoises in another ocean, which we were the only ones that were able to do that. So we were also scratching time completely there and just creating this kind of feature. Okay.
But then another question. Yes.
And now when you scan a picture, okay, now go to visual cortex, okay, when you scan a picture, you have the complex and then super complex, etc. And you have this kind of little detectors, okay, that kind of scan the image and pops whenever you find this detector, okay? So it's the same idea, the eyes move, which kind of gives you the integration to kind of say, oh, I detected it. When? Oh, there, okay? So it's not crazy.
Yeah, but no, it's not crazy. But the question is, did you take a look at those? Basically, you can look at those waveforms, right? Those basis functions. Say, what do they look like? Because if I understand correctly, you just take those basis functions which you arrive, right?
Yes, yes.
And then you can simply take your signals and convolve with those waveforms, basically.
Yes. So they look like snakes in time frequency. Like snakes in time frequency.
They look like snakes in time.
Yeah.
So
if they were like fixed in time, they would simply be band filters, okay? If they would be just this, it would be chirp detector. But basically,
so
they can look like snakes.
Sequence of changes between dominant frequencies, right?
Yes. Yes. Okay? So, so that tells you and the others why those features are less sensitive to artifacts, okay? Because something I did not tell you is that actually the EEG signal is very, very weak, and a much stronger signal is electric signal that's coming from muscle activity. Now, for those of you who are doing EEG, you know that we use a lot of electrodes and we apply an amazing algorithm called independent components analysis, which kind of takes this and tries to look for non-Gaussian projections and tries to kind of separate to the sources of the signal And so it will throw the EMG or the muscle activity to kind of 1 or 2 channels, and it will keep the EEG in other channels and even separate them based on other features, okay? I cannot do that because when I use just 2 electrodes, ICA does not work. I kind of took the dog's project just to show that this can be done, because the dog is like crazy when he's running to, to sniff, and he's even moving the forehead, so it's kind of creating a lot of EMG, and the movement of the head is obviously creating a lot of artifacts in EEG signal. But then these snakes...
In which frequencies those snakes were? Which frequencies, I mean, which bands?
It's in many bands, of course.
Well, but in which range? Which range?
But
from...
So I mentioned that we sample at 500 hertz.
Yes, but...
And I would say more that the range, the higher range, say from 100 hertz to 250 hertz, has a lot of information. Classical EEG, they kind of say, oh, there's gamma, and they low pass at 40 hertz or 70 hertz, or maybe some low pass at 120 hertz. Many low pass at 40 to avoid the 50 hertz noise. It's a huge mistake. It's a huge mistake.
Did you see this recent paper, maybe like 5 years ago? I forgot the name of the person who did it. Basically what they did, they injected the Maya blockators. Okay, they blocked the muscle activity, okay? And they were all ventilated with the certain machine, right? And they were comparing the spectra of EEG before the Maya blockator and after, okay? And the spectrum starting from 20 hertz dropped by, I don't know, by 10 dBs or so. So it basically shows that EEG has above 20 hertz, has a very, very strong muscle contamination, muscle activity.
I agree with you. So here's one mistake, okay? 10 dB is nothing. 10 dB is nothing, okay? Because even when you're looking at a signal that's coming from a neuron that's very far from the electrode, okay, we kind of think, the signals don't arrive to the electrode at all, and the electrode is very, very sensitive to a very small region, very close to the electrode, correct? So it's true that
region, but close to the electrode.
That's another reason why people use a lot of electrodes, okay? So what happens here is, of course, the signal from neurons that are very close to the electrode is much stronger. The signal from neurons that are very far from the electrode is much weaker, and the EMG signal is even much, much stronger, okay? So you're just right. I mean, yes, when you remove the EMG, the signal looks very, very different. This method apparently is not sensitive to this fact, okay? Because once you throw away, and you'll see I'm doing exactly the same now with earthquake detection, I'm throwing away the high energy components. Because I can also play with the signal, okay? So you can throw away the high energy components, which would be EMG. And suddenly you are left with other components that are not EMG. You created the beautiful separation, because the statistics is very different between EMG and EEG. And suddenly you can look at the very faint one EEG and EEGs that are far from the electrode, and suddenly there's a lot of information at high frequency. Does that make sense?
That's all very interesting. Well, the point is that it does make sense, for sure, but it so badly contradicts my own experience. Therefore, I'm like feeling very strange now. But anyway, thank you very much. We'll have a chance to talk
So
later,
let me tell you this, okay? So EEG is known for 90 years, okay? Yeah. The best work, or the most important work, was done in 1924. And now you're talking with people and they say, this doesn't make sense. We know that you cannot read the amygdala with electrodes outside. We know that you cannot read areas that are far from there. So the joke is, that some things you do only when you become full professor, because now you can do anything you want and you can argue about it. And it took me several years before people started realizing, well, it must work because, the guy can extract information that others cannot. We have some paper. I did a lot of conventional EEG, fMRI work before doing this, okay? So I started from the convention and then kind of went to the non-convention. So we have an example of recording EEG and fMRI and demonstrating that we read the amygdala much better than alpha over theta or things like this,
That's interesting. But what if, like, for
So
instance,
you can go look at my EEG papers.
I
You'll
looked
see
at
the
some. Yes,
progression.
I did look, of course. Yeah.
This is not published there, okay?
Yeah,
But you can see the pattern now, if you like. 96 pages.
But did you try to apply, for instance, your method to? Is the time taken all this time, or maybe?
Actually, we have a question from online viewers. May I take a stage? Okay, so I'm reading this. So, if brain language has higher level of entropy, is it healthier compared to brain with a lower level of entropy? Is that true? Of course, there are a lot of equivalent classes, at least two, but I'm asking about elements inside different classes.
So there was this long question. What was the last sentence?
Of course, there are lots of equivalent classes, at least two, but I'm asking about elements inside different classes.
Elements inside different classes.
I'm not sure what the author meant because, it came online.
Can
But
someone
if
explain
you had,
this?
so the basic question is: is it true that if brain language has higher level of entropy, is it healthier compared to a brain with a low level of entropy?
No. We cannot make such assumption. I definitely cannot make. I can only quantify, okay? And then let the doctors associated with behavior, with all sorts of disorders, okay? Entropy is a way to measure, okay? So Tononi's work, Tononi is equating subconscious or unconsciousness to very low entropy. So in the case of subconsciousness or unconsciousness, clearly entropy goes down, okay? But in other cases, hyperactivity may increase entropy. I'm not sure if this is healthy, okay? So this attention issues and hypersensitivity may increase entropy, but not necessarily be healthy. So, one cannot just do a one-to-one correspondence. We can talk later, okay? More questions? Yes, please. Sit down. Yeah. There's a microphone.
Thank you. Thank you for your presentation. Can you say anything about relation of your ideas with functional asymmetry of the brain? I want to add, I thought about it first, but when you have said about similarity of results of men and dogs, I thought that you can say nothing about asymmetry.
Okay, so yesterday in the document that was on the chairs, there was a paragraph just at the beginning that was talking about functional asymmetry and why it kind of makes sense to look at the difference between FP1 and FP2, okay? And I thought that this is the key feature that we are looking at until I got to a patient that has basically half of his brain removed, okay? And at the beginning, I thought it would be kind of a waste to put my electrodes on that brain because I will not see anything because I'm looking at the difference between FP1 and FP2, so I'm kind of looking at asymmetry. I had amazing brain activity, which resembled a very normal activity from that patient with half a brain, okay? So apparently there's more than just to asymmetry here. I mean, apparently some of these features may correspond to asymmetry and maybe attention issues, etc., but there are other features which do not respond to asymmetry. That's all I can tell now. There's more basic research that's needed. Not a good idea.
Yeah, you talk about brain and electrodes.
Yeah.
We saw the brain. Can you show the electrodes? Nobody understands what we are talking about.
Let me see if there's any electrode. Because we left it upstairs. We have electrodes. Just a second. So this is the electrodes that we are looking at right now. Okay, 3 electrodes. The middle one is what we call a reference. So we basically put it like this on the forehead. Later it will be a color of the skin, so it will be totally invisible. We have a little bit of electronics that connects here and connects behind the ear, and this is our sensor. And these electrodes these are medical grade electrodes. They can remain for a lot of time on the subject, the patient, etc. So they can provide really 24/7 monitoring when needed. And we have recordings from people more than 10 hours every day. And so we monitor them a lot, and we see a lot of changes. We see what's going on. I didn't mention this was mentioned before, but we kind of concentrate on patients at the lower regions of attention, or basically comatose patients, between vegetative state to minimal conscious patients. Okay? Before that, we were dealing with healthy people, so we were looking at attention, at emotional issues, etc. But now we realize that minimal consciousness patients have no way to communicate, and we can provide an amazing tool for them to communicate with the world.
Maybe you could also demonstrate some examples of the measurement you are taking, maybe from the other presentation, just pictures of...
Some pictures, so, okay. So we're going back to yesterday, so...
Not the full yesterday presentation, but some. Yesterday we had presentation for the doctors in the Institute of Neurosurgery, Bordenka.
So this is the presentation that we create of a healthy person. And now you can see here about 120 channels that we separate from 2 signals, not the 8 alpha, beta, gamma, but 120. We have here now, so each line is one of these channels. This is time, so these are the channels. As I said, that they are ordered, so these 2 channels are close by because they are highly correlated. And this is why we see kind of an ordered structure in this, and we'll see a few examples, okay? And here we separate into specific regions which we found by analyzing a lot of data, which we found to be relevant. So we have this area which we consider to be cognitive, and we see a lot of issues in cognitive, but we call it cognitive because when we deal with minimal consciousness, it's either active or not. Part of this cognitive is an area that we call executive, and I say area, it's area here. In the brain, we do not know if it is distributed or where the location is, although we have some anecdotal evidence where, for example, we kind of know now that this area has to do with medial prefrontal cortex. Why? Because they put Buddhist monks into functional MRI when they meditate, and we can correlate what we see in meditation, in their meditation and whatnot. This is the emotional area, and we see here kind of activity that, you know, this is 15 minutes, so this is like very slow activity, but you see it's quite ordered. So apparently this ordering that we did is very, very useful. Basically here we see more cognitive load, here we see lower cognitive load, and there's a lot of examples that one can show. Maybe I can show what we see so this is like cognitive activity. We see very strong executive. This is a person taking decisions. We see kind of mild activity, much stronger activity, and much less activity. And we see stress at the bottom, and we can see the connection between increased load and increased stress, whereas we see reduced load and increased stress. So for example, here, increased load, we see increased stress, but here we see reduced load and still increased stress, and this is really what we call stress. So increased load and stress are together. This is one disorder that we see in those minimal consciousness patients, namely the area that we call cognitive is not active, whereas the area that is emotional may be very active, maybe not. Another disorder is that this executive area is shut or not active in this minimal consciousness. Another disorder is this kind of diffuse of a lot of activity of many, many networks all together. And the last kind of disorder that we see is this diffusion in time. So unlike the healthy person where you saw this kind of activity and then rest, activity and then rest, someone knows why there's such rest? Why can't the brain be active like in full gas all the time? But what does it need in order to burn? It needs oxygen, okay? And it doesn't have enough oxygen to kind of do that, okay? So the brain is consuming about 20% of the body oxygen. When it's more active, it's consuming more, so it has to replenish. It's not the 1 or 2 millisecond time of refractory of each neuron, but then the large group of neurons also have to kind of rest. And in the minimal consciousness cases, we see that sometimes probably of a lack of some kind of negative feedback, there's no stopping, and a stimulation that starts here may last several minutes until it kind of decays. That's another kind of thing that we see. I could talk, maybe this is something that you may like, okay? So this is just for you, all right? So this is the difference between 2 types of anesthesia. This is like 6 patients doing IV anesthesia. You see that IV anesthesia...
What is IV?
IV is intravenous, the classical anesthesia. IV anesthesia, if you look, kind of closes the cognitive area, keeps the executive area on, and keeps the emotional area active, kind of if we go to what we saw before. It turns out that nitric oxide anesthesia closes the cognitive area, closes the emotional area, and sometimes keeps the executive, sometimes even closes it. And if we want to compare it to spectral analysis, is kind of related to what you had in mind. So this is nitric oxide as we analyze it, and this is nitric oxide as is analyzed by spectral analysis. So this is now frequencies from 0 to 250 hertz, because I mentioned we sample at 500. So we don't see a difference here. But when we look at this anesthesia, it turns out that there's a huge difference between the two, okay? So apparently the spectral analysis does not have these very fine features to separate between just anesthesia. And this is amazing because we have BIS for 50 years and we thought that this is good enough, etc., but it doesn't separate between basic 2 types of anesthesia. It's well known that nitric oxide, which unfortunately is cheaper, is very bad for the brain because it kind of, people that have dementia or beginning of dementia, after the operation, they will never come back to their brain as it was before. And now we see why, because the anesthesia actually cuts or shuts a much bigger portion of the brain and there's no way for it to recover, whereas IV does not do it. And there was no other way to see these kind of things before, and we see it with 2 electrodes. So it possibly is even more sensitive than multiple electrodes. Okay. With functional MRI, you see differences, by the way. Okay. But MRI. Any more questions? Okay.
Thank you very much.
Thank you.